Welcome to today's Ground School Explainer. Look, if you're passionate about aviation and you really want to deepen your knowledge of flying, you are in the exact right place. Today, we're going to examine the sky as if it were an invisible ocean. Doing that is going to help us master some absolutely crucial weather theories, specifically around turbulence and wind shear. Let's decode these invisible currents together, shall we?
Here's our flight plan for today. We'll start down low with low-level turbulence. Then we'll master wake turbulence. From there, we'll climb up to look at high-altitude threats like clear air and mountain waves. Then we'll descend back down to cover wind shear and microbursts before finishing up with airport weather detection systems.
All right, let's jump right into Section 1, Low-Level Turbulence Essentials. We're beginning our journey in the lower atmosphere. We're talking specifically below 15,000 feet mean sea level, where surface heating and friction generate turbulence. Now think of the air acting exactly like water flowing rapidly over rocks in a stream. Obstacles on the ground, things like hangars, trees, and rough terrain, act just like those rocks. They interfere with the normal wind flow to create what we call mechanical turbulence. When wind blows through these obstacles, especially right in the traffic pattern, it tumbles and rolls, giving you a pretty bumpy ride. And here's a good rule of thumb to keep in your back pocket. The stronger the wind, the rougher the turbulence.
Alternatively, we have convective or thermal turbulence. This happens when the ground heats up, causing invisible columns of warm air to rise. If you're climbing into this rising air, you're going to have a bumpy ride until you break through the capping stable layer. Luckily, the sky often gives us visual clues for this one. You want to keep an eye out for cumulus clouds, haze, or dust. Those are your signposts. They pinpoint exactly where those thermals are active.
To wrap up our low-level hazards, we've got frontal turbulence. Now this is a really powerful, highly concentrated force. It happens in the very narrow zone just ahead of a fast-moving cold front. You absolutely need to treat these zones with extreme respect. Why? Because they can hit your aircraft with sudden, violent updrafts reaching up to a massive 1,000 feet per minute.
Moving right along to Section 2, Mastering Wake Turbulence.
So we're moving on to a hazard generated not by the Earth itself, but by aircraft. We have to respect wake turbulence. When a plane flies, violent wingtip vortices spin off the edges of its wings, basically acting like invisible horizontal tornadoes. They drop down and occur at roughly 2-minute intervals behind a preceding aircraft. And you know, their intensity isn't just random, it's heavily driven by that preceding aircraft's weight, its speed, and its configuration.
If you want to pass your exams, and much more importantly, stay safe in the air, you need to memorize this exact profile. The absolute worst-case scenario for wake turbulence comes from an aircraft that is large, heavy, flying at a low speed with a high angle of attack and in a clean configuration, which just means the gear and flaps are up. That combination right there, that is the ultimate wake turbulence generating machine.
So, what's the game plan? How do you avoid it? Well, your best defense is a strategy we call flying into the bowl. This basically means you stay above the preceding aircraft's flight path, and you make sure to touch down well beyond its touchdown point. But listen, you have to remain hyper-vigilant if there's a quartering tailwind. A quartering tailwind is basically the most dangerous condition here because it can literally blow a lingering vortex directly into your flight path or push it right onto a parallel runway.
Okay, on to Section 3, Clear Air and Mountain Waves. Time to look at the high-altitude threats.
As we climb up to our cruising altitudes, the whole nature of this invisible ocean shifts. While it can technically happen at any altitude, clear air turbulence, or CAT, generally occurs above 15,000 feet. It happens when a really fast-moving jet stream rubs against slower-moving air. That friction creates a violent, turbulent mixing zone. You can usually expect it near jet streams, which, by the way, you can sometimes spot by looking for long streams of cirrus clouds, but it remains highly elusive.
And that brings us to the downright scariest aspect of CAT. It gives you absolutely zero visual warning. Because it involves non-convective clouds, the sky can look perfectly smooth right up until the second it hits. This makes it incredibly difficult to forecast. It's just a sudden, unforecastable jolt. So, yeah, always keep those seatbelts fastened.
Our other big high-altitude hazard happens over mountainous terrain. When stable air crosses a mountain barrier, the airflow tends to form intense, layered waves on the leeward or downwind side. Now, for these mountain waves to form, you need at least 20 knots of wind blowing perpendicular to the mountain range. If there's enough moisture in the air, you actually get some really cool visual clues. You want to look out for rotor clouds, lens-shaped lenticular clouds, or cap clouds just hovering near the peaks. But don't let the pretty clouds fool you.
If winds exceed 40 knots, these waves can extend up to 100 miles away from the mountain and create severely strong turbulence. So you want to follow this exact avoidance procedure. Depending on your aircraft's performance, begin your climb at least 100 miles out. You absolutely must fly at least 3,000 to 5,000 feet above the mountain peak. And finally, always approach the ridge at a 45-degree angle. That last part is absolutely vital because it permits a safer escape route if the downdrafts suddenly become too severe for your plane to outclimb. Always leave yourself an out.
That brings us to Section 4, Wind Shear and Microbursts, the localized approach dangers.
As we start our simulated descent back toward the airport, we have to talk about wind shear. This is a sudden, drastic shift in wind speed and direction that can dangerously alter both your airspeed and your altitude. It's super sneaky because it can be triggered by several different things: jet streams, frontal zones, and low-level temperature inversions. But actually, there is one specific cause, convective precipitation, that leads us to the most dangerous localized weather event in all of aviation.
Let's break down the anatomy of a microburst. Convective precipitation basically induces an intense, localized downdraft. This massive column of air plummets toward the surface, hits the ground, and violently spreads outward in all directions. This creates extreme vertical and horizontal wind shear. It is exceptionally hazardous to all aircraft, but it is incredibly deadly when you are low and slow, like when you're within 1,000 feet of the ground on your approach or departure.
Let's put the shear power of a microburst into perspective, just by looking at the numbers. While average peak winds are about 25 knots, and in extreme cases they can go way over 100 knots, flying through a microburst can hit your aircraft with a sudden 45-knot headwind change. And that's immediately followed by a devastating downdraft that can be as strong as 6,000 feet per minute. Let that sink in. 6,000 feet per minute. Most light aircraft literally cannot outclimb a sink rate like that.
Now, the one saving grace is that a microburst's lifespan is highly concentrated. The entire event usually only lasts about 15 minutes. Once it first hits the surface, it intensifies for about 5 minutes. Its absolute maximum, most destructive peak happens right in that tight 2 to 4 minute window. It hits hard, it hits fast, and then it completely dissipates.
All right, final section. Section 5, Airport Weather Detection Systems. Let's talk about your electronic co-pilots. Because these approach hazards are so localized and severe, modern airports are equipped with highly specific detection systems to warn you before you unknowingly fly right into one. Let's compare two of these real-life lifesavers. First up is the LLWS, or Low-Level Wind Shear Alert System. This system uses an array of anemometers placed strategically all around the airport. They send wind readings to a central computer every 10 seconds. If any reading differs from the average by at least 15 knots, boom, an alert is issued to air traffic control. On the other hand, TDWR, Terminal Doppler Weather Radar, uses a much more powerful, narrower radar beam. This paints an incredibly detailed, real-time picture of developing thunderstorms at high-risk airports.
Mastering these weather principles isn't just about cramming to pass your ground school written test, you know? It's really about shifting how you view the sky. It's about anticipating that invisible ocean around you, visualizing the mechanical rapids tumbling over those hangars, or recognizing the signs of a massive localized downdraft from a microburst before you're in it. So, with these tools in your mental flight bag, how are you going to adapt your next pre-flight weather briefing to ensure you are absolutely never caught off guard? Think about it. Thanks for joining me for this explainer, and hey, stay safe up there.